The electrical grid is complex, with many factors that can affect performance. That includes power factor. Power factor, the measure of electrical efficiency expressed as a ratio of real to apparent power, should be optimized for better grid performance. In fact, a power factor under 0.95 can incur additional charges from utility companies. Let's explore how power capacitors improve your power factor, efficiency, and provide substantial benefits to the electrical system. The power triangle, with legs representing apparent power in kVA, real power in kilowatts, and reactive power in kVAR, is highly useful for understanding the capacitor's effect on power factor. All electrical loads draw apparent power, measured in two components: real power and reactive power. The system's power factor is the ratio of real to apparent power, with the distance between them, the triangle's vertical leg, representing reactive power. The longer and reactive leg of the triangle, or the more reactive power the generator is providing the system, the lower your system's power factor. A power capacitor contributes reactive power to the system, shortening this leg of the triangle, improving an electrical system's power factor and increasing efficiency. Capacitors deliver numerous benefits to an electrical system as a result of this added reactive power. They reduce the thermal burden on generators, transformers, and lines by lowering the kVAR demand. This means additional loads can be added to the system without requiring system upgrades. Furthermore, adding capacitors near your load provides kVAR that the generator no longer has to supply, and which does not have to transfer through transmission lines. As the impedance in transmission lines causes losses, the capacitor's proximity to the load reduces or eliminates line losses. Because capacitors reduce the system's reactive current needs, applying them to a system results in a voltage rise from the point of installation back to the voltage source. Capacitors are used in industrial low-voltage applications, medium voltage distribution systems, and high-voltage transmission systems. In principle, they are simple in purpose and construction. They store electrical energy and are composed of conductive metallic plates, or foils, separated by an insulating material or film. Optimal capacitance comes through minimizing the space between the plates and maximizing the surface area of the two plates. Capacitors are typically installed in banks or arrays of multiple capacitor units combined in series and parallel connections to meet maximum operating voltage and achieve the necessary kVAR requirements. There are several common types of banks used to meet specific needs. Pole-mounted banks are easy to install on distribution lines, maintain, and locate for optimal performance. Mobile banks can be transported to locations on the grid for rapid deployment and system flexibility. Metal-enclosed banks utilize a metallic housing as a protective barrier, and open-air substation banks use a range of configurable, scalable frame structures to meet application needs. For more information on Eaton's comprehensive line of capacitor banks, visit eaton.com.